In the second part of today's lecture, we're going to look at actor-critic methods, or more generally, variance reduction methods or policy gradient methods. We call the policy gradient. Policy gradient, unlike reinforce, which is basically the on-to-color rollout of the policy gradient, is this expectation over the sum over time steps, and then you look at the discounted reward to go, GT. And we say the policy gradient, or in other words, the gradient of the expected reward, that's this term, is equal to this nice expectation we sum over time steps and reinforce actions based on the discount reward to go from that time step. And now this is estimated in the last lecture using reinforce. So reinforce basically just estimate this by sampling a trajectory and computing this, and then say, okay, that's our gradient. But it doesn't really work that well because it has very high variance. So that basically means that we need a lot of samples, and to get good convergence, we need to do a lot of batches together, and we need to deal with very noisy gradients that go everywhere. So in average, it's going to go to the right point, but it's just going to be so noisy that you often aren't able to control it, and you need very low learning rate, for example, to be able to get an improvement. So ideally, we want to reduce this variance and get more stable results. So how can we do this? Let's start off with the first method, which is baselines. This is done by subtracting a value from the discount reward to go. So instead of reinforcing based on the reward to go, we now increase the probability of actions based on the reward to go minus some term bt. So why is this allowed? So the idea here is that the expectation of the baseline is 0 when you multiply it with this nice term. So why is this? So the expectation when you take an action and then you compute the gradient of log probability and you multiply that with this baseline, like what is the expectation of this term? So let's first sum, which is an expectation, over all actions. And recall that this gradient of a log probability is the gradient of that probability divided by the probability itself. It's just using the chain rule, the derivative of the log probability. And we also saw this last lecture. Now also, like we did last lecture, we can just divide this term by that term, because they are equal, so we can just divide it because it's equal to 1 when you divide it. That leaves us with this term, right? Because we divide it, we are left with this term. And one thing that we should note is, and this is also an assumption that we make about this baseline, is that we can actually move this baseline out of the summation, because we assume that the baseline is not dependent on the actions. The actions don't influence what the baseline does. So we can move it out of the summation. We can also move the gradient out of the summation because it's a linear operator. Now what happens is that we have a sum over probability distribution, over all options of the probability distribution. And as we know, the sum of a probability distribution of all options of the probability distribution, that's just 1, because probability distribution should sum to 1. So in other words, this is equal to this baseline times its gradient times 1. And because the gradient of a constant, that's just equal to 0. So the intuition here is that the expected value of this baseline is 0, because it's not dependent on the action, and we can just move it out. Right, so that's very nice. We know now a way to change this objective function by simply subtracting some value b that doesn't depend on the action. So what should this value be? Here we choose a value function. The value function is very related to the Q function. So the value function is also called the state value function, and the Q function is also sometimes called the state action value function. So the value function is basically the expected value of your discount reward to go, but only dependent on the state. So in the state, you execute using the policy an action, and then you compute the discount reward to go in expectation. So you keep performing this policy whenever you execute an action. So instead of already knowing what action you take, like in the Q function, you do not yet know what action to take, and you use a policy to sample it. So there is this clear relation to the Q function, right? So it's like taking with the policy an action in the state and then computing the Q function. So this is a very simple way to rewrite one in another. So we can just, ideally, we would just use this one as our baseline. So we subtract the discounted reward to go with the value function, which is the expected reward to go. So what does this kind of mean? So what's the difference here between reinforce and using this baseline? In reinforce, we were looking at chess for this problem, right? So we act, we do some action within chess, so we move one piece, and then maybe in like 50 time steps we get a reward. We won or we lost, right? So how do we now reinforce? How do we choose what rewards what actions to increase? So this can be determined based on the algorithm you use. So in reinforce, what we basically just do is we execute an action and then keep on running your policy until you get in some state and you say, oh, I won in the state. So that's a positive reward. But that's of course a bit noisy, because you could also, somewhere else in the whole sequence of steps after that, it turns out that you actually lost. So it's a random reward. With this baseline, what changes, instead of taking just the fact that you won, you're also computing the expected value in that state. Or in other words, the expected probability that you will win in the end. Now if it turns out that you thought you were going to win with 63% chance and you actually won, that means that you did 37% better than you expected. In other words, this baseline is basically saying, okay, how much better did I do than I expected that I would do when I chose this action? So you increase the actions based on how much better you did than you expected to do. And this is actually a lower variance estimate. So why is this? It's because if you already expected to do very well, then that's not a lot of useful knowledge. But if you actually did much better than you expected, then that's really something that you should be increasing. That's a really useful action to take. It turned out to be a very nice idea to take that action. So this is a much more, it's basically saying, if you did better than expected, much better than expected, that's going to that was a very useful choice. While if you did worse than expected, that should really be this decrease that action, even though you might have gotten a positive reward somewhere in the end. So how do we find this baseline, this value function? Well, we just do it like we did in the deep Q learning lecture. We train a neural network to approximate this value function. So not the Q function, but the value function V. And we just do it with regression. Here, what we can do is we can use rollouts. We can just say, we just estimate that based on the reward to go that we actually get. So, for example, you say you sample the trajectory, we got a reward to go, and as the value function is the estimated reward to go, the expected reward to go, not estimated. Then you can just say, let's just regress our value function to the actual to the samples that we got when executing our policy. So that's one way to do it, but usually what people actually do is, just like in deep Q learning, we use bootstrapping. So we use a bootstrapped error that we derived. So just like there is an optimal Q function, there's also an optimal value function, which allows us to derive this very nice regression problem where you, don't forget, that detects your target, but your target is now going to be this bootstrap error. So the reward in the next state plus the expected value you will get in the next state. So that's this term. So again, you can train this network just like you would in deep Q learning, but you have to compensate for the fact that you're dealing with a value function, not a state action value function or the Q function. So, if you understand Q learning, you're going to understand what this means, except that you now are dealing with just states and not states and actions. So, reinforce with a baseline is going to be a very simple algorithm, but now you are actually training two parameters, because you're both training the policy and the baseline. So what you do is we simply sample the trajectory, just like in reinforce. And first what we're going to do is we're going to update our baseline. So we update our baseline based just on this equation where we use this bootstrap error. And we have to minimize it because it's we want to minimize the error, right? And this way we get a better estimate of the value function. For a policy, what we're going to do is we're going to just reinforce, but the difference is that we now subtract this value function that we estimated, v phi. That way we get a much better low variance gradient to use gradient ascent on. Here we also actually have two different learning rates for the baseline, or the critic, and the actor. It is a very simple algorithm. The only thing we really change is that we now have this value function that we change, which we subtract as a baseline from the discounted reward to go that we find. So can we do better than this baseline trick? Yes, we can actually. We call a Q function the state action value function, which is the expected value of the discount reward to go. And also recall the definition of the policy gradient, the gradient of the discount reward. It has this sum of time steps of discounted reward to go times this reinforced step, so the reinforced log probability. So clearly the Q function estimates exactly the discount reward to go. So can we make use of that? Yes, we can. In fact, we can actually just literally replace this GT by the critic, which is the Q function. So simply, all this is saying, this is not a proof of this statement, but we can simply replace the discount reward to go, which is going to be sampled, with the expected value based from this Q function. And we say here that this is the critic. This is basically going to say how well we did, and this is going to be the actor, which is basically the policy, right? And it turns out that this has much more lower variance. So why is this? Let's return to the chess problem. In reinforce, we say we execute an action and we see what happens. Okay, maybe we won, right? That's a random reward. Actor-Critic is a bit different. Instead of saying I won, we say I think I'll win with 0.63 probability if I take this action. So that's a much lower variance signal, right? Because you already know what exactly the expectation is. It's not like a random reward, so it's not like some noise that happens within executing it, or you have a very good opponent that did some random actions that confuse you, and now you won or you lost. So all this randomness that happens after you take an action is now just suddenly gone, because you use the expected value instead of taking a random reward. So if we can actually manage to really faithfully reproduce this discount reward to go with the Q function, we can get a very low estimate, very low variance estimate of a gradient by using the Q function instead of the sampled reward to go. So the Actor-Critic algorithm, the simplest one actually, is reinforcing based on your Q function, your state action value function, or in other words, based on the expected reward you will think you will get. Can we make this even better? So we just saw one way to reduce variance, which was using a baseline. Can we not just apply this here too? Yeah, why not? We can actually just do that. So we can actually subtract the baseline, in this case the value function baseline, from our critic. And this has much lower variance as well. And so what is this thing called? It's actually called the difference between the critic and this baseline is called the advantage. And this still is called the actor. So we usually call this method the advantage Actor-Critic. And it's actually right now one of the most popular reinforcement algorithms around. I think most of the state-of-the-art methods use this advantage function in some way, in some shape or form. So it's a very important equation. So what's the difference of using this advantage instead of this Q function or just this critic? In normal Actor-Critic we say, I think I'll win with 63% probability if I take this action. But if we subtract the value function, which is basically saying, in this state, I expect to get, like, for example, 60% probability to win, and the difference between what you expect to get when you take an action and the value the value you expect to get in the state might be, for example, 3%. So it's basically saying, if I take this action, how much more likely do I think I will be to win, right? So it's basically saying it's all an estimation of values, but in this case, it's a difference between what you expect you will get expect when you take an action and what you expect to get in general. So it's basically saying what do I expect my advantage to be when I take this action compared to other actions that I could take. This all happens based on estimating the value of a state and the value of taking an action in a state. So, to summarize, the Q function, normal critic algorithms, Actor-Critic algorithms, just reinforce based on expected reward, while advantage Actor-Critic algorithms reinforce based on expected increase in reward after taking an action. And this has actually much lower variance also than the normal Actor-Critic algorithms. So how are we going to compute this method? So you will probably not be surprised that we're going to estimate this baseline by using a neural network, just like we did in the previous part when we introduced baselines. So how are we now going to estimate the Q function? Should we just use Q-learning here? Yeah, kind of, but it's actually not even that necessary because of this relation between the Q function and the value function. You can actually estimate, it's a bit biased, it's kind of a bit wrong, but we can roughly estimate the Q function of taking an action in a state by looking at the next reward and then computing the value function in the next state, so using this recursion. And because of the way the Q function and the value function interact, this is actually a very good estimate of your Q function. Now there is one thing that you might have noticed, which is that it says estimate v pi with v phi, so it's a neural network, and it says here biased. So why is it biased? Now, if you look at this equation, in here you say we have the Q function of the policy pi minus the value function of policy pi. So the Actor-Critic algorithm reinforces based on the Q value of the policy pi. But if we now estimate it using value functions estimators, so using our parameters phi instead of using the true Q function, then this is no longer a correct policy gradient. It's no longer true in expectation that these two are equal. So if we would here fill in this equation, it's no longer an accurate estimation of our policy gradient. And why is this? It's because we cannot completely accurately, with 100% accuracy, estimate this value function. So whenever we make a mistake in estimating using v phi the true value function v pi, we're actually going to introduce bias within our algorithm. So in Actor-Critic algorithms, we exchange bias by estimating these value functions by variance, because we have way lower variance. We can now compute the advantage function, which is we're going to use a lot, which is basically just this term over here as the reward plus the value function in the next state, so that's this term, minus the baseline, which is this term. And we're going to estimate it using our network parameters of the critic, which are phi. So to summarize the advantage Actor-Critic algorithm, we estimate the policy gradient using a biased version, but we use this advantage function instead of the discount reward to go that we sample using a Monte Carlo rollout. The advantage function is the critic, which is basically an estimated Q function, minus the baseline. And so, why do we do this? We trade off variance, so we have lower variance, and so better sample efficiency, but we have a bit more bias. So things are kind of wrong, but because we have so much lower variance, we're still going to find usually a much better policy this way. We're going to see two different versions of this Actor-Critic algorithm. They are actually very similar. We first start off with the Bates mode algorithm, which looks more like reinforce. In fact, if you remember the algorithm from the baselines, it's very similar. So in fact, the first two lines are exactly the same. We sample a trajectory using a current policy, and then we update a critic based on our bootstrapped estimate to minimize the error. That's just the same as we did in baselines. Then we're going to update the actor, the policy, and we're going to do this not based on an estimate of the discount reward to go, but based on this advantage function. So we use our critic to estimate the expected increase in reward whenever we execute this action in the state. And all we need for that is the current state, next reward, and the next state. That's all we need for that. So there's actually another way to implement this algorithm, Actor-Critic, which is online Actor-Critic. Online Actor-Critic, we actually do just like in deep Q learning, where we update after every action instead of after every trajectory. This is not possible in reinforce because we have to accurately estimate the discount reward to go. But because we now just estimate the reward to go based on this advantage function, we can actually also do this algorithm online. So we select an action according to our policy. So compare this to the deep Q learning algorithm. In deep Q learning, we would use epsilon greedy to select actions, but now we already have a stochastic way to select actions, namely our stochastic policy. Then we're going to go to the next state. So we sample next state and next reward. Then we're going to update the critic. We do this just by taking one single step. So we see the value function of the state, and then use a target which is based on the next reward and the value function next state. This is actually also very much just like how you would learn the Q function in deep Q learning. Just try to compare this line with deep Q learning in the deep Q learning online mode algorithm. Then finally we update the actor. So we compute the advantage function of this transition, and we then increase that probability or decrease it based on what the advantage function says. And we can just keep looping this. So right now, this is of course a pretty poor algorithm because all the algorithms I introduced are pretty poor without many tricks behind it. In this case, we only use a single sample to estimate both the critic and the actor. And usually we would really want to batch up things. However, if we just take multiple time steps and we just collect data from over multiple time steps, then we get correlated mini batches. So recall maybe that you in machine learning always need to update based on identically and independently distributed IID data or IID mini batches. But if you collect batches over time, then they're going to be correlated. And in fact, it's going to be so correlated that you can't really properly train it. There are many methods that try to reduce this. One of these is a very famous A2C algorithm, which is asynchronous advantage actor-critic. Wait, no, that's actually the synchronous one. Sorry, that's A3C. A2C is a synchronous advantage actor-critic algorithm. What this does is that we have multiple agents that act in different copies of the same environment, and we just collect their experience together and update based on that. This is a very efficient method. It actually does really well. It's pretty simple to implement compared to many other reinforcement learning methods that really require a lot of tricks, but it still does fairly well if you tune the networks properly. So in this section, in this part of the lecture, we looked at variance reduction methods for policy gradients. First, we introduced baselines, which subtract a value from the descending where to go, and it gives an unbiased and pretty low variance estimate of the gradient. Then we looked at Actor-Critic. It reinforces based on the expected value of taking an action. This is a bit biased, but it has pretty low variance, so it's pretty good. But even better is the advantage Actor-Critic. It reinforces based on the difference in expected value. So if it does better than you actually expect to do, if you expect to do better than you expected, that's confusing, sorry. Then that's what you reinforce on. So you increase based on how much better you think you will do. And if you can estimate the critic well, this can be a very accurate and low variance gradient. Next, we're going to look at world models in the final part of deep reinforcement learning.